Okay? All right, so I forgot to show you this picture, but I hope that makes sense. So the car is going, we want to stop it in 2 meters, and the force is 20 degrees below the horizontal. Okay? So anyway, you didn't really need that picture, but it doesn't hurt. All right, now a completely new topic. Now we want to talk about rotation about a fixed axis. So we're going to learn the kinetic energy of rotation. So when am I talking about rotation about a fixed axis? So what we're saying, so pretend I have a bicycle tie, a wheel, right? And I can somehow hold the axis, you know, and so I spin it, and so the axis doesn't move. So the wheel is just rotating about that fixed axis. That's all. All righty. So, wow. What we're going to say then, so this is not a bicycle wheel, but it's just a blob, right? And we're going to say that, this blob is made up of lots of different molecules. And we're just going to look at 3 of the molecules. Obviously, there's a very large number of molecules. So this is the rotation axis. It's rotating counterclockwise, right? And remember what we learned a long time ago for rotational motion. This is the radius, this is the velocity, or the tangential velocity. So this is a right angle, this is a right angle, that's a right angle. All right? Okay, here we go. So we want to calculate the total rotational, that's why there's a little r there, kinetic energy. And we're only going to do 3 particles because it's going to be bad enough. All right, so what's the kinetic energy from this guy? 1/2 m1 v1 squared. This one, 1/2 m2 v2 squared, and so forth. So we're just going to say 1/2 m1 v1 squared plus 1/2 m2 v2 squared plus 1/2 m3 v3 squared plus on and on and on. Okay? Now that gets sort of tiring to write it like that. So let's just be lazy. What do you say? Let's just write 1/2 sum over I mi vi squared. So, all right, so this means m1 v1 squared plus m, it's a sum, so you add, right, plus m2 v2 squared, da 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 da. So I actually goes from 1 to however many molecules there are. We don't usually bother writing this I equals 1 to n because it's understood. Now, we're talking about rotational motion, right? So we really ought to use V equals r omega, our good old friend from a long time ago. So let's substitute. We have 1/2 m1 v1 squared, v1 squared, r1 squared omega squared plus 1/2 m2 r2 squared omega squared plus 1/2 m3 r3 squared omega squared plus on and on and on. Now, which we can be lazy and write 1/2 sum mi ri squared omega squared. Now, wonderful. Now here's a question. Why don't, I have to subscript the m's because there's different m's. I have to subscript the r's and the v's. How come I don't have to subscript the omega? How come I don't have like an omega 1, omega 2, omega 3? Well, you should know that by now, right, from what we did a long time ago. Every particle has the same omega, right? Omega is the angular velocity. Every particle has the same angular velocity. So that's why I don't have to subscript the omega. Okay, I'm going to write this a little differently. I'm going to write this as 1/2 parentheses sum mi ri squared omega squared. All right, that doesn't hurt anything. Now, wait a minute. If you've been paying attention, what is this? You should know that. What's the sum mi? What's the sum mr squared? This is rotational inertia. So this is 1/2 I omega squared. So that's the kinetic energy of rotation. 1/2 I omega squared. Okay, there you go. Now, that's a very nice way to derive that equation, but you know, we could have done it the lazy way. I mean, we could have done it all right, so there it is, right? So the rotational kinetic energy, 1/2 I omega squared, where I, you know from a long time ago. Now here's another way we could have done it, which is totally awesome. Okay, so here, you know, translation just means like that, right? So the translational kinetic energy, 1/2 mv squared. Okay, that's translational. Well, what we want is rotational. Okay, so 1/2 becomes a half, no kidding. What's the rotational version of m? I. What's the rotational version of v? Omega. So see, all you have to do is just one-to-one, you know, one-to-one relationship. I mean, this is the better way to do it, but this works, so why not do it, right? You know, m is I, v comes omega. So that's what I mean, you know, once you know this equation, if you know that, which you really need to know that, all right? Once you know that, this is free. This is free. Okay. Now, we talked about rolling motion at some time in the past. We want to talk about it again. But now we're going to use our energy equations. So let's talk about rolling motion with our energy equations. So we've seen this slide before. It's nothing new, right? This is the pure translation. This is the pure, what did I just say? Yeah, no, sorry. This is the pure translation, right? This is the pure rotation. When you add this and this, you get rolling motion. Okay, so that's nothing new. You've seen that before. All right, so let's get an equation for it. So what is the kinetic energy of pure translation? It's 1/2 mv squared. What is the kinetic energy of pure rotation? It's 1/2 I omega squared. So that is the kinetic energy of rolling motion. You know, just as you would expect, there's two pieces, right? There's the translational part and there's the rotational part. So when you have something rolling, there's two pieces to it. I mean, what can you say, right? So there's a translation, there's a rotation. So you add them together and you get rolling. So there's two terms for the kinetic energy of rolling motion. And you'll probably use that in a lab near the end of the semester, right here. I mean, we'll see. Okay, so that's very important. Okay, now we're going to shift our gears again. We're going to talk about heat, thermal energy, thermal energy. So that's supposed to be the surface of the sun or something like that. All right, let's say you're in Ace Hardware. You just bought a can of paint. They put it on a paint shaking machine so you don't have to stir it so much when you get home. So what happens to the kinetic energy of the paint molecules when a can of paint is shaken or mixed at a paint store? Okay, so pause your video and figure it out. All right, so we're back. So think about it. You have these paint molecules, they're being shaken. So kinetic energy, you know, is 1/2 mv squared. So the velocity is increasing. So what happens to the kinetic energy? It obviously increases. That makes good sense. All right. Now therefore, what happens to the temperature of the paint when it's shaken? And temperature is a measure of thermal energy. Well, we don't have to vote on that. It's sort of obvious, right? If the kinetic energy is getting larger and larger and larger, you know, the temperature is going to increase, right? So the thermal energy increases. Okay, so we kind of want to talk about, well, you'll see. So we want to talk about macroscopic versus microscopic. So, macroscopic. This means you're looking at the system as a whole, okay, like a person or something like that. Moving, okay? So this is the blob, this big blob. Mass M moving with some velocity. So that's called macroscopic. Now, if you had a really good microscope, you could look inside that blob and you see molecules or atoms or something, right? And let's say molecules. And the molecules are held together by molecular bonds, and a very good model for a molecular bond is a spring, which you've heard before. So molecules in motion, right? Because they're moving around, right? They're moving around because they're held together by springs, so they're moving around. So the molecules are in motion, each has a kinetic energy. Now the molecular bonds stretch and compress, right? And so there's potential energy associated with each system of molecules. Okay, so the bonds have potential energy, elastic potential energy. Great. Okay, so basically here, we're just considering the kinetic energy of motion. And here we're having kinetic energy of the individual molecules and the potential energy of the systems, right, the bonds. So kinetic energy, kinetic and potential energy. Okay, so just looking at the microscopic, right? So the microscopic, we have kinetic energy and potential energy. And that's what we call thermal, okay? That's what we call thermal energy. It's the microscopic kinetic energy and the microscopic potential energy. That's what we call thermal energy. Okay? So, remember we used to just have delta E was delta U plus delta K. Well now, since we're looking at the blob with a microscope, we also can consider the thermal energy. All right, so now we have delta E, delta U, delta K, delta E therm. Okay, because this is changing, right? This is changing. So there's a new term in our energy equation, that delta E therm. Okay, so this makes pretty good sense. And we know how to calculate that, right? Delta U for the gravity is just mg delta H. Delta K is just, the change in kinetic energy, 1/2 mv squared. But how do you actually calculate delta E therm? How do you do that? I mean, it indicates that something's getting hotter or colder, but how do you calculate it? I mean, we're not studying thermodynamics. How do you calculate delta E therm? Well, that's what we want to talk about now. So we'll talk about two examples. So let's say that this is a heavy box. Doesn't look like it is, but just pretend it is. Heavy box. And we're pulling it at a constant speed to the right with this force. Now, there's friction, and since the box is moving, there's kinetic friction. Agree? All right. So what do we do? Okay. Well, let's see. Here's our equation. Work equals delta U. Okay. This is delta E, right? Delta E equals work, which equals delta U plus delta K plus delta E therm. Great. All right. So what's delta U? What's the change in gravitational potential energy? Well, 0, right? It's not changing its elevation or anything like that. Okay. What's delta K? Well, it's constant speed, so the kinetic energy doesn't change, right? So that means that the work equals delta E therm, right? Okay, we're getting there. Okay, but all right. So what's the work? Okay, so the work, well, it depends on what force you're talking about, So if you're talking about this force, the work is just F delta X, right? FD times the angle. Now, we just want to use magnitudes now. We're not worrying about the directions. So the magnitude of F equals the magnitude of this, right? Because it's constant speed, so that magnitude equals that magnitude. So just magnitudes are equal. We're going to say that equals Fk delta x. All right, just magnitudes. Okay, now, and we're going to say that it's positive work, right? All right. So what are we saying? We're saying that when you do something like this, when you're pulling this along the floor, the box is going to get hotter and the floor is going to get hotter. So we're saying that, so if we're saying the work is, if we're saying that the work is positive, you're saying that delta E therm is positive. Again, this is magnitudes, right? Magnitudes. And so the delta E therm is positive because the floor gets hotter and the box gets hotter. Okay? And if we wanted to calculate that more, you know, we would say, so it's Fk delta x, so it's mu k normal delta x, which is mu k mg delta x, right? So we can calculate these delta E therms, that's all I'm trying to say. Okay, let's do another one. Yeah, I just said that. Okay, let's do a different one. Let's do pulling an object through water at constant speed. Okay, so again, what's delta E therm? Well, you know, oh, sorry, not yet. Well, okay, sorry. Okay, so again, this is the equation for delta E. So delta E equals work equals delta U plus delta K plus delta E therm. All right, now, this is not changing, right? This is not changing, constant speed, just like the last one, right? So delta E therm is the work. Now, the work is the force times the delta x. Now, same thing, magnitudes only, so I don't care about the directions, just magnitudes. This, right, the magnitude of F has to be the same as magnitude of D. D is drag, like we had before. Okay, so drag times delta x. And that's all there really is to it. Okay. So I guess what I'm trying to say is, you know, there's no great way to calculate delta E therm unless you know that delta E therm equals the work. And then you know how to calculate work from the formula, right, that you learned earlier. So you have to use the fact that delta E therm equals the work to calculate delta E therm. All right, that's all. Now here again, this is going to be positive. So what does it mean? It means that the surrounding water is going to get a little bit hotter. It means that the object's going to get a little hotter. That's what it means. And that shouldn't surprise you. I mean, you don't remember this because you're too young, but when the United States sent up a rocket to the moon or wherever, and then the astronauts come back in the space capsule, and so when the space capsule comes through the Earth's atmosphere, you know, it's plowing through a lot of air molecules, going really, really fast. So the bottom of the space capsule like just turns red because it's so incredibly hot. So you might want to look that up one of these days. Just Google it or something to see a picture of that. It's pretty cool. All right, let's see. Let's just keep going, I guess. All right, let's talk about conservation of energy. Now, look at, you know, when we talked about conservation of momentum, we had, you know, isolated systems and all that. No more of this isolated system stuff. Now, there's no restrictions. We're talking about conservation of energy of all systems, everything. So this is kind of a big deal, right? And it is a big deal. I mean, it's used in all branches of science. Energy is conserved. It's incredibly important. Okay, here we go, people. All right, so we're going to begin with our favorite equation. So I got to do some math, sorry, but we got to do it. You got to do it, right? Okay, so I'm going to ignore this part. I'm just going to use this, kind of like what we did before, you know. Okay, so I'm going to start with, so delta U plus delta K plus delta E therm, remember, equals work. Okay? Great. Now, what's delta U? U final minus U initial. Oops, minus U initial. What's delta K? K final minus K initial. All right, and we just got to leave that alone, right? Plus delta E therm equals work. All right, if I feel like it, I can put all the, I don't like minus signs, yeah? So I'm going to put all my minus signs on the other side. Okay, is that all right? Sure. So I have U final plus K final plus delta E therm equals U initial plus K initial plus work, right? Okay, and I don't really, now this is kind of weird because it has the final on the left and the initial on the right. I really want to have the initial on the right and the final on the left because, you know, I read from left to right. So initial left, final right makes more sense to me, right? So whatever. So U initial plus K initial plus work equals U final plus K final plus delta E therm. All right, so I didn't really do anything all that earth shaking, but I promise you, and you'll see, that this is more helpful to write it like this than the top one. Okay, so I did my algebra and I showed you I didn't cheat and I came up with this. And that's a very useful formula. In fact, we're going to see that you can solve many, many complicated problems with that equation. So let's do an easy one, and then we'll do a hard one. So let's do the easy one first. Super easy, but that's okay. Nothing wrong with that. All right. Oh yeah, ta-da, sorry. So that's kind of a big deal, all right? Woohoo, look at that. Okay, so here we have a tall building, not too tall, because we want to ignore drag. So we have sort of a tall building, and the system is going to be the building plus Earth, and you know we're going to include Earth because we're going to include the gravitational potential energy, right? So you have to include the Earth, you know. We're not going to have any drag. Keep it simple, so this is going to be 0. Keep it simple, right? Keep it simple. Okay, we're including the Earth, and so the gravitational forces, that's not an external force, right? Because it's including it in our system. So that means that the work is 0 as well, right? Right? When you drop something, if the Earth is in the system, there's no external force pulling it down. So this is 0. So all we have is that. Isn't that nice? So simple, love it. So we have U initial plus K initial equals U final plus K final. That's all. Okay, now, so we're going to stand at the top of the building, and we don't have a stopwatch. So, you know, we're not going to be able to measure velocities without a stopwatch, right? Well, you wait, okay? So all I have is I have a meter stick. I have a meter stick so I can measure how high I am. I have a meter stick and I have a ball I'm going to drop. All right, that's it. Okay, so let's do it. So let's have a table. I'll fill in that table. So we have UG in joules, energy in joules, kinetic energy in joules, and then we have the total energy. So we have UG in joules plus K in joules. All right. So we have potential energy, kinetic energy, total energy. Okay. So let's say at the top, we're at the top of the building. Let's just say that somebody, so we know we measure, remember, UG is mgh, okay? So we measure how high we are, we measure the mass of the ball, and magically it comes out to be 10 joules. Whatever. I'm just making these numbers up, right? All right, so we hold the ball at rest at the top of the building, so the kinetic energy is 0, because kinetic energy is 1/2 mv squared, all right? And so then the sum is just 10. Now notice, U initial plus K initial equals U final plus K final. That means it's constant, right? So the total energy never changes. That's the important thing. The total energy never changes. Okay, then let's see. Then let's go halfway. All right, so we go halfway. So what's the potential energy halfway? Well, if it's all the way, it's at the top of the building, it's 10. Halfway, it's 5, right? Because it depends on h. And we're halfway down, so it's 5. Okay, now, we don't have a stopwatch. We can't measure the kinetic energy. But wait a second. We know that the total energy is constant. So this is 10. It's always 10, right? It's constant. Well, if the total energy, which is potential plus kinetic, is 10, the potential is 5, what does kinetic have to be? 5! So look at that. So what does that mean? That means just by using conservation of energy, we can figure out the kinetic energy anywhere we want, which means basically we know we can measure the velocity. That's kind of cool, right? And then at the bottom, when I say bottom, I mean right before it hits the ground, right before it hits the ground. So the potential energy is 0, right, because h is 0. The total energy, it doesn't change, it's still 10, right? So it's a kinetic energy, 10. So there you go. So without using a stopwatch, you can know the velocities anywhere you want, just by using conservation of energy. Now, you may have noticed in the book that Randy Knight loves these bar charts. He likes all these different types of energy diagrams. So this is called a bar chart. So this is energy here, all right? So here, this is the total energy, the kinetic plus potential, and it's constant, right? So it's constant. And you can see at the top of the building, there was no kinetic, there's only potential. So the potential was equal to the total, which is exactly what we have here. The potential equals the total. Halfway down, the potential is half, so that means that the kinetic has to be the other half, which is exactly what we had. And the total is the same. Then at the bottom, there's no potential energy. The total energy is the same, so the kinetic has to be the total, okay? Which is completely agrees with that. All right, let's see. Let's do an example. And this is a real life problem, believe it or not. So everybody read it, please. Think about it. Okay, in screeching to a halt, a car leaves skid marks 65 meters long. The coefficient of kinetic friction is 0.71. How fast was the car going before the driver applied the brakes? All right, now, first of all, why is it kinetic friction? Because the car is sliding, right? So it's kinetic friction. Now think about it. Boy, whenever you see the coefficient of friction, that means force, right? So you're thinking in your head, there's forces, right? There's forces. There's a distance, right? There's a distance, 65 meters. There's speeds, right? There's speeds. It says screeching to a halt. So there's an initial velocity and there's a final velocity. Remember, when you see velocities, what should you think in your head? Well, I mean, it depends on the problem. It could be momentum, but it could be kinetic energy too, right? It could be momentum, though, I admit it. It just depends on the problem. Okay, so all sorts of things. Now, forces and distances. What is that? Forces and distances. That's work, right? That's work, And so, maybe it's going to help us, maybe it's not. I don't know. We're going to find out. Okay? Okay, and kinetic energies. All right, so all I'm saying is what we want to do is we want to evaluate this thing. So here we go. Let's see. Now, wait a second. What's going to be the system? What's going to be the system? We want to make it kind of simple. All right? Easier is better. So let's include the Earth. You're going to include the Earth, right? Because we want to include gravitational potential energy, right? So, but let's include the road too. Because, you know, if we include the road, then is the frictional force external? If we include the road? No. So if we include the road, we won't have to worry about that. That's nice, right? All right, let's do it. Okay, let's do it. So you write it down. Ui plus Ki plus W equals U final plus K final plus delta E therm. The system is the road, earth, car. All right. Now, it's a level road, you assume, so the potential energy initial equals potential energy final, which we're going to call 0 because it's 0 height. So here, so that's 0. Okay, this is just 1/2 mv initial squared. Okay, we're going to call that 0. All right, we're going to call that 0. K final. Now look at it, it stops, so K final is 0. And what's delta E therm? Well, we did this a little while ago, right? So we said that delta E therm equals the frictional force times the displacement, right? And we know that Fk is mu k normal. And we know that's mu k. The normal is just the weight, so mu k mg times delta x. All right, so we just do it, right? So this stuff equals that stuff. So therefore, we have 1/2 mv initial squared equals mu k mg delta x. That's it. All right. So, yeah, okay. All right. So now we're trying to solve, what are we trying to solve for? The speed, right? The initial speed. Okay, now look at what's beautiful about this thing. The masses divide, the masses cancel, right? So goodbye masses. We want to solve for the velocity, multiply both sides by 2. Then take the square root. Here's your answer. Okay, let me write that nicely. So initial velocity equals square root of 2 mu k g delta x. Okay. Now, where do you use this in the real world? Well, maybe you've seen it in a TV show. You know, let's say somebody was involved in an accident and they had skid marks. Well, what do the police generally do? They measure the length of the skid marks. Okay? So they measure the length of the skid marks, and then, you know, they kind of look at the road, they kind of look at the tire, how much tread is left, and so they somehow figure out a good approximation for mu k. And then what do? They use the laws of physics to figure out what the initial velocity was. And if the guy was speeding, they're in big trouble. All right, now, what's so awesome about this method? Notice it does not include mass. I mean, this would be a disaster if it included mass. Then the policeman or a woman, you know, would have to would have to know the mass of the car, and, you know, make a lot of trouble, right? But this does not depend on the mass of the vehicle at all. It just depends on the friction and how far the skid marks are. So, pretty good problem. All right, let's quit. How long was that?